Hello, we are Team Taser, Group 13, and our project is Mars Rover Suspension System. Our group members are Rivas, Emilio Adame, Ramon Aleman, Sebastian Torres, and Talal Alsaedi. Our table of contents include an introduction, assumptions, a free body diagram, our hand calculations, our optimization, and conclusions. Moving on into our introduction, in this project we must design, analyze, and optimize the suspension system of a Mars rover. A rover must have a suspension system that has the ability to resist static and fatigue failure. The outcomes of this project are to calculate the value and location of the maximum stress in the suspension system and check for the static yielding and fracture, as well as calculate the fatigue resistance of the suspension system and optimize design that meets the safety requirements with the lightest weight possible. Some assumptions involved in this project were the angle between the shock and tube does not change, the tube does not deflect, assume small strain, and assume a design safety factor of 3. Moving on to our free body diagram, we can see the reaction forces being applied to the tube by a 850-pound force at an angle of 75 degrees, causing reaction forces in the y direction as well as the x direction. In our shear diagram, we can see a force of AY at 273.7 pounds being applied constantly throughout the tube until it reaches 8 inches, where our 850-pound force is being reacted, giving a shear force of negative 547.36 and being applied constantly throughout from 8 inches to 12, and then another reaction force of 347.36 pound force. Given our moment diagram, you can see a peak at 2189.6 at 8 inches and descends linearly until 12 inches. As for our axial diagram, it shows reaction forces in the x direction, which are equal and opposite at 220 pounds force. Moving on to our hand calculations, using the free body diagram from above, we were able to determine the reaction forces being applied on the tube by summing the forces, summing the moments at A, which led us to give reaction forces By at 547.36 pound force, and then summing the forces at X, which gave us AX and BX, a reaction force of 220 pound force, and then summing the forces in the Y direction, giving us a AY of 273.7 pound force. Continuing our hand calculations, we needed to determine our fatigue safety factor, but first we needed to solve for our endurance limit and modified endurance limit using the equations and tables from chapter 6. Given our endurance limit SE equal to 0.5 times the ultimate tensile strength, which equaled 90 ksi, times 0.5 gave us a endurance limit of 45 ksi, and then solving for a surface factor Ka, which equaled constant A times ultimate tensile strength to the power of constant B, and constant A and constant B could be found on the table of hot rolled steel, which were 14.4 and negative 0.718, and applying those to the equation, we get a surface factor of 0.569 ksi, as was, and for a size factor Kb, we found it to only equal 1, and the loading factor Kc we found to be 0.85 for axial loading and 1 for bending. as was a reliability factor KE to be equal to 0.620. Now, having those numerical values, we can solve for our modified endurance limit, which equals KE times KB times KC times KD times KE times our endurance limit, and we get a value of 13.5 KSI. Continuing our hand calculations, using figure 618 on page 293 of our mechanical design book, we determined F to have a value of 0.86 in order to solve the following equations. A equals F times ultimate tensile strength to the squared divided by our endurance limit equaled 443.76, and B, which equaled negative 1/3 log of F times ultimate tensile strength divided by our endurance limit, which equaled a value of negative 0.2528. Plugging into our fatigue safety factor equation, which is SF over A to the power of 1 over B, we got a 6,303,952. In our optimization, in order to have the best design, we needed to calculate the stresses that were going to be applied on the tubular arm at each size, then compare those stresses of the safety parameters of the yielding stress to the material and applying calculated stress to be less than our safety yielding, which is stress X less than our stress Y. And after applying these boundaries, we noticed that the first size option did not meet our standards, so we went through trial and error until we found suitable parameters for our design. Then we calculated the life cycle of each size arm and compared it to the safety parameters of life cycles allowed, which is NF2 to be greater than NF safety design. And using those two parameters, we chose the dimensions that were best suitable to not over design. And the next few slides will explain how we were able to determine these values using an Excel spreadsheet and Mathematica to verify our hand calculations, as well as determine which two will be optimal for our design. Our optimization continued. Using an Excel, we were able to create a code to optimize our design, where our moment of inertia was found using moment of inertias were found using table A8, properties of round tubing, and we found stress X for each diameter using stress X equals F over A plus F of X times the diameter of each tubing divided by 2 over the second moment of inertia. And you will see that later in our Excel spreadsheet. Next, we found the safety yielding stress with the equation stress on VCs to be greater than or equal to our yielding stress over our design safety factor. And from our design project, we have fatigue safety factor N equals 3 and design life ND equals 500,000 cycles. We can solve for N, which is 3 times 100,000, which equaled 1,500,000. Doing so gave us an idea of where our design will be best utilized when solving for the number of cycles using the equation mentioned above, NF equals SF over A to the power of 1 over B. To verify our hand calculations, we used Mathematica to solving for our reaction forces, which gave us a BY force of 547.358, AX force of 219.996, and AY force of 273.68. And using Mathematica again, we can solve for our modified SE. And plugging it into Mathematica, we can see that we get the same as our hand calculations, which would be 45 SE, our endurance limit to be 45 KSI, and our modified SE to be at 13.4971. Using this Excel spreadsheet, we were able to determine which parameters were best suitable for our design, which were an outer diameter of 1.5, a thickness of 0.25, area of 0.982, a moment of inertia of 0.199, and stress X at 8.47694, and our cycles to failure at 6,303,952, which was not over-designed or under-designed. Moving on to our conclusions. In summary, we simplified the problem into free body diagrams, and doing so we are able to determine the reaction forces and moment forces. With these forces, we were able to construct the shear, moment, and axial diagram, which led us to determine our critical point. Assume the reaction forces on the x-axis for the tubular arm were equal, and with that we analyzed the longer side of the arm and put the critical point at the piston. Then we calculate the life cycle of each size arm and compared it to the safety parameters of life cycles allowed. And using those two parameters, we chose from the parameters we established by using the safety factors given in the project, which were 1.5 diameter and 1/4 thickness tubing, which allowed us to be used to be optimal for our arm. Using these dimensions, we found them reasonable because as the tubing diameter increased, their yield strength also increased, and it was seen true in the number of cycles. As the diameter increased, their number of cycles to failure also increased. Some problems encountered while completing this project were our time management between classes, projects, work, family issues, and several other factors. At several occasions, our team was unable to meet because of these issues, which may have affected the outcome of understanding this project. Although upon meeting and discussing the project, we had problems calculating the state of stress and which tube sizing would be best for our design. Another problem faced was that our group was not very experienced in the utilization of symbolic solving software, such as Mathematica, MathCAD. Although we were very knowledgeable on Excel, those softwares required us to use more time into learning these softwares, which made the time into understanding this project having constraints on it.